Hey guys, it's Tori from Hat's Tutors, and today we're going to be learning how to name alkenes. So what are alkenes? Well, alkenes have the formula of CnH2n. That means that for every carbon there are two hydrogen. And that, if you recall, is the same as the formula of cycloalkanes. But what exactly are they? Well, they are hydrocarbons, similar to alkanes, but they are joined by one or more double bonds. That means that they are unsaturated hydrocarbons because they have double bonds instead of only single bonds. So, saturated hydrocarbons means that they are hydrocarbons with only single bonds, whereas alkenes are unsaturated hydrocarbons because they have double bonds. So let's go over some properties of alkenes. Alkenes are nonpolar, but they are more reactive than alkanes. So let's just go over to ethene here, and we can see here that is two carbons and 4 hydrogens, and it follows perfectly with CnH2n, the general formula. And as you can see here, it is nonpolar, similar to ethane, which is also nonpolar. So we can conclude that both alkanes and alkenes are nonpolar. However, ethene is more reactive than ethane, and that is true for all alkenes, and that is due to the nature of the double bond. According to a theory called valence bond theory, I won't go too in depth on this, but you can Google it or search it up on your own. Basically, single bonds are what we call sigma bonds. Sigma bonds. Whereas double bonds are pi bonds. And pi bonds are a lot more reactive than sigma bonds. And that is basically the general principle of this theory. And also, they have lower boiling points than alkanes. And that is due to the lower London dispersion forces found within alkenes. And that's because, as you can see here, there are less atoms in this ethene when compared to ethane, which is C2H6. And remember, London dispersion forces are determined by, well, one factor of the London dispersion forces is the number of atoms. So naming alkenes. Similar to alkanes, you want to find the longest continuous chain of atoms. But this time, it has to contain the alkene, which means that it contains a double bond. To be more specific here, alkenes actually have more priority than alkanes. So if you have, I'm going to use a line diagram as we learned last time. If you have a separate chain of alkene, sorry, this is a bad example. But anyways, if you have a separate chain of alkenes that has less carbon atoms than an alkane, and the alkene itself is a longer chain, you would still name it based off the alkene because alkenes have higher priority. So then, you want to number the main chain in a way so that the carbon number of the double bond is reduced. This is similar to numbering substituents that we covered in the last PowerPoint. Numbering substituents. And then you change the usual ending of ane to ene and insert the carbon number between the body name of the alkane and the ene. Separate the number with dashes on both sides. I'll show you with an example. I'll show you what this looks like in an example right after. And lastly, you want to name the branches and substituents. So let's move on to the example. As you can see here, let's just ignore the name for now, but let's take a look at this alkene. As you can see here, the longest chain containing the alkene is either this one or this one. It doesn't really make a difference. But let's just say we go with the horizontal one. And we want to prioritize the alkene. So let's number it from right to left. 1, 2, 3, 4. What this means is that the alkene, the double bond, will be on the first carbon. So we want to write how I derive this is basically there are 4 carbons. That means that usually it'll be a butane. But we follow the rule of changing the ane to an ene. And then we have to insert the carbon number between. When it's the number 1, you can usually omit it. But I just like to have it in this example to show you guys. And then of course we name the substituent of ethane changing it to ethyl. So 2-ethyl but 1-ene. Isomers. Isomers are compounds of the same formula but arranged differently. Today we're going to focus on geometric isomers because they are the most important isomers for alkenes. In particular, the cis-trans isomers. Cis-trans isomers are two different structural arrangements for alkenes relative to the double bond. 2-butene, this is what we would name as but2-ene. This is the better way, but2-ene. And basically, let's look here. As you can see here, the two methyl groups are on different sides for the cis and trans system. The cis system is where the two groups with priority are on the same side, and the trans, the two groups with priority, are on opposite sides. So the methyl groups are priority, and for the trans system, opposite sides, cis, the same side. The EZ designation system. The EZ designation system is the new version of the cis-trans system. Z corresponds to cis, and E corresponds to trans. Add bracket E or bracket Z before the full name of the compound separated with a dash. As you can see here, the two groups with higher priority are known as Z, similar to the cis system. And the two groups with high priority are on opposite sides, which is the E system, similar to trans. A quick tip for remembering it is the same side. This sounds like the same side, but it starts with Z, so you know that Z means that it's the same side. So how do we determine priority? Well, the first rule is the atom with higher atomic number receives higher priority. If we go back here, we can see that out of the two groups connected to this carbon, one is connected by the carbon and one is connected by hydrogen. We know that the carbon has a higher atomic number than hydrogen, so we know that in the cis-2-butene case, we know that these two groups are of higher priority, and the trans-2-butene, these two groups are of higher priority. Now the second rule is a bit more complicated. If there's a tie, so what this means is, let's just say we have a double bond over here and 4 groups attached. All 4 groups start with a carbon. That means there's a tie. We look at then we look at the atoms attached to the original atom until a difference is found. So let's just say for this carbon, there's X, X, X. Just X is denoting like basically any element, and for this carbon it's X, X, Y. We know that, let's just say Y has higher priority than X. That means that this group has more priority than this group. Similar case here, if we have like X, X, Y, and then maybe 2 Y's here, and since Y has more priority than X, that means that the Y here would have more priority than this X, since these two cancel out, basically. You could think of it that way. That means that this lower group has priority, so that means that these two bottom groups have priority, so that means this is a cis system. And now we have a note here where the double bonded atoms count twice. This is a note for the future when we get into functional groups. Basically, some functional groups are double bonded, and that means that the double bonded atom counts twice for this priority system. So let's name the following. Let's use the EZ system because that is the preferred system. So let's see here. Let's identify the longest chain, and I think this is the longest chain here. Let's count the number of carbons. 1, 2, 3, 4, 5, 6. So that's a hexene. And let's see, the double bond is on the third carbon. So hex 3-ene is our base. And let's identify if it's E or Z. Well, the groups with priority. Obviously on this side, this is a group with priority. But on this side, the left side, we have to use the second rule of determining priority, which is let's compare the other atoms attached to the original carbon. So as we can see here, this carbon has 3 hydrogens attached, whereas this carbon has 2 hydrogens attached and 1 carbon. Well, we've spotted a difference. This carbon is different from this hydrogen, and carbon has a higher atomic number, so that means that this bottom group has priority. As we know, this would be the E system, or if you cis-trans, it would be the trans system. So it would be E. Also, some instructors prefer if you have the double bonded number, like the number of the carbon double bond, before the E. I feel that's a bit redundant, but some teachers would prefer it that way, so let's just put it there. 3E, 3-methyl, hex 3-ene. Sorry, I'll rewrite it again, the full name. 3E, 3-methyl, hex 3ene. Now let's take a look at this one. This is the longest chain, and this is also a hexene. Another hex 3ene, in fact. So hex 3ene. And determining priority for this one is a lot easier. We can see that these two groups have priority because the carbon has more priority than the hydrogen. Simple as that. And they are on the same side, so that would be Z. So 3Z hex 3ene. Now let's draw the following. Z heptuene and 2,3-dimethyl cyclopentene. So let's start with Z heptuene first. Let's draw a heptane. And let's put a double bond on the second carbon. So this is the second carbon. Let's put a double bond here. And now we know that that's a Z formation. So we might have to fix our structure. But let's just take a look here. So we know that this, we can imagine that there's a hydrogen here. We can imagine there's a hydrogen here. As you can see here, we've actually kind of drawn a E formation because they're on opposite sides. So let's draw the Z formation here. The Z formation would look something like this. 1, 4, 5, 6, 7. So this heptene, this is Z heptuene. As you can see here, the double bond on the second carbon, and the two groups of priority, which is this group and this group, are on the same side. Because we could just imagine there's a hydrogen here, and these are the groups of priority on the same side. Let's tackle the second one now. 2,3-dimethyl cyclopentene. So let's draw a cyclopentane first. And we know that there's a double bond, which is why it's called cyclopentene. And so let's put a double bond here. And we know that double bond is priority, so this would be 1, and this would be 2, and this would be 3. So let's draw 2 methyls here. And that's it. It's as simple as that. And if you are wondering why is there no Z or E before the cyclopentene? Well, remember that for cyclopentene structure, like cyclostructures in general, they have to be drawn like this. You can't have this on this side, like this carbon on the other side, because then it would not be a cyclostructure anymore. Hope that makes sense. And that's it for today. Thank you so much for watching this video, and I hope you learned something. As always, if you have any questions, leave it in the comments. Have a great day, and stay safe.